Alright, let's blast through the neutron stars and black holes unit. I'm going to try to fit these 21 slides into one video, so hopefully less than a minute per slide. Here we go! Alright, so a neutron star. So after we have a type 2 supernova, big explosion, what's left over is the core. And if you remember from that unit, all of the protons and electrons were squeezed together and formed neutrons, so that essentially everything in the core was a neutron. Of course, neutrons can only get so close. Gravity can only pull them so close, and so the size of a neutron star is as small as it's going to get unless something else takes over. So that forms from the neutronization of the core, and this doesn't get destroyed during the supernova because it's thought that the shock wave from the explosion starts at the surface here, at the edge of the core, and blows out. So whatever's inside kind of remains secure and stable together. These stars are really small, about 20 kilometers, so what, from here to DC, even less maybe? Yet they're very massive, way more massive than the Earth. What that means is if you fit all that mass into a small space, you get extreme density. And so if you were to take a little marble-sized piece of this material, it would weigh up to upwards of 1 million or 100 million tons. Insanely large amount of material stuck in a small space. A typical average person would weigh tens of billions of tons. Um, and it's a nice little physics term, but you don't need to know this. Due to conservation of angular momentum, these stars rotate very rapidly. How do they get to rotate so fast? Think of an ice skater. An ice skater, part of the routine, they'll start spinning with their arms out, and then as they pull their arms in, they spin faster. So that's conserving angular momentum, we say. Same idea, why these stars spin faster. They also have very strong magnetic fields because as they collapse down, the magnetic field lines squeeze together, making the field strength larger. And we have a picture here of the magnetic field, and there's poles of the magnetic field. So here you got field lines that way, and then that way, and here are the poles. And at the poles, you got these beams of radiation just shooting out, high energy electromagnetic radiation, X-rays, etc. And if these poles happen to point towards the Earth, we'll see that bright light. Typically what happens is the stars will rotate, and sort of like a lighthouse, a beacon of light, these poles will sweep by the Earth, and we'll see flash, 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 flash as it rotates past the Earth, and these lights hit us. And since they spin so rapidly, the flashing of the pole lights will be very rapid, like oftentimes many more than one per second. What are some of the other things being shot out besides light? We got particles being shot out, charged particles, which are most often left over after that supernova explosion that left the neutron star behind. Those are also accelerated towards the surrounding nebula from this magnetic field, and they're seen as a pulsar wind. This wind excites this gas that's around them, the leftover supernova gas. I don't have a picture, but it lights the gas up, making them look like bright nebula. All the pretty nebula pictures you've seen. And as I said, because the neutron stars are spinning so quickly, the period of the pulsars are very short, usually less than a second, like maybe a 3/10 of a second or 300ths of a second. So they flip by 3 to 30 per second. And of course, this is too fast for the human eye to detect. TVs are typically 30 frames per second, and all they are 30 still pictures per second. But at that speed, when those pictures are meshed together, it looks like fluid motion. So we need instruments to be able to see this short period. For example, here's a picture when the pulsar is off, meaning the pole is not pointing towards us, and here when it's pointing towards us. So, and just a little bit of logic for you. All pulsars are neutron stars. If you find a pulsar, you know it's a neutron star because only neutron stars can spin this fast, and that we know of anyway, and give off this bright these bright amounts of light from the magnetic poles. But not all neutron stars are pulsars because not all of the poles are facing Earth. If they're not facing Earth, we can't see the light from them. So, yeah. Sometimes, often actually, neutron stars are in binary systems. They have neighbors, and especially if one of them is well, I mean, sorry. So yeah, they can accrete large amounts of matter from their partner. So um, if one of them is close enough, or if they're close enough to each other, I should say. And as they steal this material, this is kind of like the white dwarf near its neighbor, its like binary neighbor. Same idea. Same thing happens. It forms an accretion disk, and um, large X-ray bursts happen when this event occurs. Kind of like a white dwarf nova. We call it an X-ray burster. And see, you see here kind of a picture of that. So you got a companion star, and the neutron star is stealing matter from it, giving off X-rays and jets of energy. And so neutron stars can spin about 1,000 times a second. How do they spin so fast? Maybe because of stealing mass with a partner, it increases the spin rate. Alright, so now we're going to transition into black holes, but before we talk about black holes, let's talk a little bit about Einstein's theory of relativity. So first off, there's this thing called light, and we've talked a lot about light because basically all of astronomy is studying light. So the speed of light, which we call lowercase c, is the upper limit on the speeds of all known matter. In fact, matter actually can't travel at the speed of light. You need massless things like photons to actually travel at this speed. And a difference between light and actual matter is that velocities add for objects with mass. So, example, if you're in a car going 100 kilometers per hour and someone throws a ball or shoots a bullet 1,000 kilometers per hour relative to the car, like in the car, someone standing on the ground sees this move at the sum of the two speeds. 1,000 plus 100 is 1,100. But light doesn't behave this way. So this is like the car up here, and this flashlight is like the gun up here. So the flashlight shoots out photons of light, and if the spaceship is traveling at 0.1 c, and the light beam is traveling at c, because c is the speed of light, does the observer see 1.1 c? 1 plus 0.1? Nope. This still looks like c. If the spaceship is traveling 0.9 c, like 9/10 the speed of light, and you shoot a beam of light out from a flashlight, still that looks like it's traveling at the speed of light from observer. Weird stuff. And Einstein thought about this stuff. He started thinking about it when he was really young. He proposed, based on his thought experiments, the special theory of relativity back in 1905, almost 110 years ago now. And here are some of the highlights of the theory. First off, again, the speed of light is the maximum speed in the universe, and all observers measure light to be traveling at the same speed regardless of the speed of the observer. That's the whole velocities don't add deal I just talked about. Also, there is no absolute frame of reference in the universe. For example, the Earth is not the center of the universe, unlike we have thought in our sort of recent history. Because of this, only relative velocities between observers matter. How fast two observers are traveling relative to each other. How fast is the Earth orbiting around the Sun relative to the Sun? How fast is the Sun orbiting around the galaxy relative to the galaxy? And here's the most important, well, not necessarily the most important, but one of the most mind-blowing, surprising outcomes of this theory is that space and time are essentially one entity. If you warp space, you're also going to warp time, and that's just weird. Later, after becoming famous for his special theory of relativity and continuing on with his research, he added gravity to the special theory of relativity, making the general theory of relativity. And what's new to this is that, again, gravity is included, and the statement that a gravitational field is indistinguishable from an accelerated frame of reference. What does that mean? Well, if you are in an elevator orbiting the Earth, or just like being held up above the Earth is going to pull you down into the floor of the elevator, and you're going to feel that force pulling you into the floor. Well, if you're notice there's no windows in the elevator, so you can't actually tell that there's an Earth out here. You don't know which situation you're in, A or B. So then, now let's take you way out in deep space. You're not near any planet or star or anything, so there's really no gravity pulling you. But instead, there's a spaceship up here, and tied to the spaceship is a rope, and the spaceship accelerates that way at, we'll say, you want to mimic the Earth, and it's going to accelerate at 9.8 meters per second because hopefully you learned in one of your science classes that the acceleration due to gravity on the Earth is 9.8 meters per second squared. So if the spaceship goes whoosh like that, you have some inertia. You just kind of want to stay still. So the elevator floor is going to go with the elevator that way, and it's going to push up against your feet, and you're going to feel that as a force, and it's going to feel just like you're being pulled down into it by gravity. So there's no difference. It's all relative. Based on this and the fact that space and time are essentially one and the same, like I said before, if you warp space, you also warp time. And a good analogy, not a perfect analogy, but a good analogy for how this works is you take a rubber sheet and you spread it out over a table, like a table with there's no hard surface on the table. It's just the frame of the table. Like maybe this was a glass picnic table and you took the glass part out and replaced it with a rubber sheet. So then the rubber sheet's nice, stretched out and flat, nothing warping it. But then you put a mass on it, like a rock or something mimicking a planet. Notice that it will warp the sheet. It'll pull the sheet down, making a deep sort of impression or hole there. Now along comes another little object, like a spaceship or a moon or an asteroid, per se, and it's going to follow the curved path. It might even orbit. It could like just crash into it, or it might orbit around a little bit. So that's a good analogy for how mass warps space and time. For a black hole, this curvature is intense. So here's no warping. Here's a small mass warping just a little bit, and you can see the little people are being gently pulled towards here. So they're cluttering or clustering around here. If you have like maybe a star warping it quite a bit, it has a strong gravitational pull, and more people are here. Notice that's easy for them to escape if they have enough speed. But a black hole warps this extremely, just a lot. And there's a point, we're going to talk about this in more detail, where it's like a point of no return, and you can't get back out. Here's a nice picture where a black hole is actually warping space-time enough that light bends significantly. So you got light from a star behind it. So here's us observing from our telescope down here. Here's a black hole between us and another faraway star. Light from the star goes, and so this really distorts the star. It doesn't look like a star because the light's going in all these different directions. Pretty crazy. Alright, black holes. So, what is a black hole? Well, one way we can probably get a black hole is through large neutron stars. So basically all you need to make a black hole is you need to pack enough matter into a small enough volume that gravity can overcome any opposing pressure, even the neutron degeneracy pressure that keeps a neutron star stable. So if you take a neutron star that is in excess of 3 solar masses, then the neutrons can no longer resist gravity. Gravity's like, I win. And it's squeezed down even further. Now, if you go even bigger than 3 solar masses, over 25 solar masses, this is enough to create a black hole. So how do you create a black hole? Anything could become a black hole. Essentially, a black hole is where, oops, hold on a sec. Alright, fixed a little typo there. So again, anything could become a black hole. Um, Basically, if you squeeze something down um, while keeping the mass the same, the escape speed for the surface of that body increases. So let's just say for some reason you are being you let's say your mass is about, I don't know, 100 kilograms or so. It's a good average mass maybe for a person. It's actually pretty big for a person. But anyway, let's say you're being squeezed down. Your mass isn't changing, but your volume is changing. You're getting squeezed smaller and smaller. Um, the gravity that your mass creates is going to be the same, the same distance from you. But since you're being squeezed smaller, let me actually draw this here. So here's you normally, and here's your center. And so something here is going to experience a certain force of gravity from you. Now let's squeeze you smaller. Here's your center. Now this distance is no longer on your surface. It's like out here. So you're still going to experience the same force as before, but now since you're smaller, something could be on you closer to your center, and so the force of gravity is going to be bigger there. There's a point where the force of gravity, even on you, is so strong that light can't escape you. Even light can't escape. But you have to be squeezed small enough so that your surface is a short enough distance from your center that this happens. You squeeze anything small enough so that, and we're going to learn this term in a slide or two, so that it's inside the event horizon. The event horizon is based on a mass. So if you have a certain amount of mass, it's going to have a certain event horizon, a certain distance from the center. If all of the mass is squeezed inside the event horizon, then this event horizon basically says that light can't escape from this distance. If light is outside this distance, it could escape. If light is inside the distance, it can't escape. And if light can't escape, nothing can escape, because light is the fastest that anything can travel. So, for example, what's the Earth's event horizon? Well, if the Earth could be compressed to the size of a white seedless grape, then the escape speed would at that point be greater than, at the surface of the Earth, that would be greater than the speed of light. So the Earth needs to be about that small to fit inside the event horizon and start to become a black hole. Typical black holes are about the size of a green pea and contain about 25 solar masses. So the radius at which the escape speed of an object equals c is known as the Schwarzschild radius, and this is the event horizon. For the Earth, it's 1 centimeter. So if you have enough mass to equal the mass of the Earth, the event horizon is 1 centimeter. Anything inside 1 centimeter has no hope of escaping. If you're outside 1 centimeter, you can build up enough speed to eventually escape, but it's going to be tough. Common misconception about black holes is that they suck everything into themselves like vacuums. No, this is actually not true. Black holes are just mass, objects of mass like anything else, like a star, planet, you or me. It's just that all of their mass is squeezed inside their event horizon. So it's possible to reach a point where you can't escape from them. Whereas, like the Earth as it is now, its event horizon is 1 centimeter from the center. There's no way to get 1 centimeter because you have to dig through all the Earths, all through the ground and through the mantle, and so there's just no way to get that close to the center where you couldn't escape, because you can't even get down there anyway. Yeah, so objects can easily orbit a black hole, and most objects do. More objects orbit the Earth and the Sun, currently anyway, than they do crashing into them. So, same idea with a black hole. And if something actually does become stuck in a trajectory where they are going to crash into a black hole, they get spaghettified. They get vertically stretched and horizontally squeezed. Alright. Another cool thing about space travel near black holes. So when light escapes the nearby gravitational tug of a black hole, the light redshifts because it gives up energy and changes wavelength. So the speed of light must remain constant. And in order for that to happen, as it loses energy, it has to change wavelength. so it gets red shifted. So yellow light would become more red, and then eventually become infrared, and then radio. Um, and so the closer you get, the closer the light starts from the event horizon, the more it's redshifted, to the point where if you're right at the event horizon, it's infinitely redshifted, and you actually can't see that light at all. Same thing happens with time, because time is linked to the wavelength of these lights, right? If a time ticks by every time a peak of the wavelength goes by, then the longer the wavelength, the longer the time it is. So the only way to see a clock is with light from the clock. And if the clock, like I said, ticks periodically with the waves, then if the frequency decreases because it's redshifting, the passage of time looks like it decreases. So the closer something gets to the event horizon, the slower time seems to pass for it. Not for that object, but from someone observing the object. So if you're sinking into a black hole, nothing changes for you. Time just flows by normally. But if someone's watching you enter a black hole, the closer you get, the slower time seems to pass. So it's going to look like you're in slow motion, slower, 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 until you reach the event horizon when you'd actually stop. But at that point, the light would never reach you anyway, so you can't see that. So it's kind of weird. So what do we think is inside this event horizon? If nothing can escape it, we can't actually ever get any information from in there. What do we think is in there? Well, based on the general theory of relativity, it's predicted that all of the matter will collapse down into a singularity, or an infinitely small point. But you have to take this with a grain of salt, because that's really, well, most likely impossible. When a singularity or an infinity comes up in trying to make some theories for physics, then that usually means that the theories are not complete. Something wrong with the theory, or we just don't understand enough. So unfortunately, this is not a question where you can get any closure, because we just don't know enough about our laws of physics are not complete enough to actually describe what's going on down there. String theory is making a strong attempt to explain this, but it's not a complete theory yet by any means. And finally, as I said before, the light that can escape, the light that doesn't go into the event horizon of a black hole, will be warped tremendously. So that's one way we can have evidence that black holes exist, by seeing this tremendous warping of light. We also can look at the X-rays being emitted by binary companions and predict that, well, we can't see anything here. We can see the energy around it, but we can't see, like, right at the very center. So maybe this is a black hole stealing matter from its binary companion. And also it's thought that supermassive black holes are at the centers of galaxies, and we can actually start to see evidence for that in our own galaxy. Yeah, so that's it for neutron stars and black holes. Sort of a longish video, but I think I went through it in pretty quick time. And till next time, bye bye.